This is section 2 of formation of differential equation. In our first section, we learned how to solve formation of differential equations. We want to continue with other functions or other equations, using them or differentiating them to form differential equation. So let's take, if you are asked to form differential equation from y is equal to x plus a over x. We were told in the first section that when we are given any equation, when we are asked to derive the differential equation or form the differential equation from it, we first of all have to identify the variables and then the arbitrary constants. So we have y being the dependent variable, x being the independent variable, and a is the only arbitrary constant present. So we have only one arbitrary constant in this equation. So since we have one arbitrary constant, it means we have to differentiate the equation once. Okay, but to proceed, we have this function, this equation on the right, the expression on the right. We have x, the variable x in the denominator, dividing a. So what all that we do is, before we differentiate, we have to write it. We have to reciprocate the x so that it will appear in a horizontal form, so that there will be no fraction. Okay, so let's proceed. So we have to rearrange. So we can rewrite this as y is equal to x plus, to find the reciprocal of this, we have a x to the power -1 before we start the differentiation. So we have it in this way. We want it to be simple. So if you have it this form, it is easy to differentiate. So we name this one, this first equation 1. Okay, secondly, what we do is we differentiate. So we differentiate the dependent variable y with respect to the independent variable x. So if you differentiate y with respect to x, you will get dy dx is equal to, the first term on the right is having x is having the power. So if you differentiate, it means 1 will multiply the whole term. So it will be 1 times x is the power, then subtract 1 from the power, then you get 1 minus 1 plus, then with this we have to also use the -1 to multiply the term again. So -1 times ax with the power -1, and after which we subtract 1 from it. So we have performed the differentiation, but you have to simplify it. So we have 1 times any number is that number. So x raised to the power 1 minus 1 is 0. So it is x raised to the power 0. Positive and negative, positive and negative. So positive times negative is negative. 1 times a is a x raised to the power -1 minus 1 is -2. So we have x raised to the power 0, and we know that x raised to the power 0 is equal to 1, provided x is not equal to 0. Provided x is not equal to 0, x raised to the power 0 is 1 minus, then we have a x raised to the power -2. Now, because we have the power x to the power -2, the power of x is -2, we can find the reciprocal so that we'll get a positive index. Okay, so we have to find the reciprocal of this, and we have x raised to the power 2. So we have dy dx equal to 1 minus a over x squared. And we said that to form differential equation, we have to eliminate the arbitrary constant. So we still have the arbitrary constant present in the equation. So what I will do is, you have to find a way of eliminating the arbitrary constant. So what we do here is, you can make a the subject from this equation. So we can proceed to make a the subject. from this equation. So if you make a the subject from this equation, we are going to get dy. What we do is we send this to the left hand side because it is negative. So we have a over x squared, and then equals to 1 minus, first of all, send the dy dx to the right hand side. So we have 1 minus dy dx. Multiply 2 by x squared, we will get x squared times a over x squared equal to 1 times x squared minus x squared times y dx. So this x squared times a over x squared equal to 1 times x squared minus x squared times dy dx. We said we are multiplying 2 by x squared, so this cancels that, and we have a standing alone. 1 times x squared gives us x squared minus x squared times dy dx gives us x squared dy dx. Okay, so now since we have a being the subject, we can use a can also be obtained in equation 1. In equation 1 we have y is equal to x plus a over x. So we can, or in this equation we have a y equal to x raised to the power 1 plus a x raised to the power negative 1. But actually I will prefer this, the main equation, so I can name this equation star. This is the simplified form. So I'll make name the equation star. We'll substitute or put. You can say put, simply put. So put equation 2 into equation star. So if you have equation star, we have y. In equation star we have y is equal to x plus a over x. So what we do is we are going to replace the a. So we have y is equal to x plus a. A is x squared minus x squared dy dx. X squared minus x squared dy dx all over, then all over x. So this is the a. This a. Okay, so from here we are going to simplify. So we have x plus x squared. We have x squared here, x squared here. So it's factorize x squared out. So we have x squared out. Then we have 1 minus dy dx all over x. And this x will cancel one of these x. Then we have x plus 1 minus dy dx equals y. Because so now we have, after multiplying 2 by x squared dy dx, we put equation 2 into equation star. We will now get y equal to x plus, then a is x squared minus d square y dx squared times x all over x according to equation star. So we factorize x squared out. We have x squared. Once we factorize x squared out, we left with 1 in the bracket. And then here it will left with dy dx in bracket all over x. So if you cancel out, x takes one of the x out from here, and then we have finally x plus 1, because 1 times 1 is 1. Sorry, we have x. We have x times dy dx is x dy dx. So all that we do is So we have x bracket open 1 minus dy dx. 1 minus dy dx. And what we can also do is we can, if we expand, we get x plus x times x is x times dy dx is negative x dy dx. Now x plus x is 2x. X plus x is 2x. So minus x dy dx. So these are differential equations. We can decide to make dy dx a subject or leave it in this form. It's still a differential equation. So basically that is what to do for that. Now let's look at another example. We are going to form differential equation from trigonometric functions like cos, sine, and then also exponential functions. So let's take for example, if you are asked to form differential equation from y is equal to a cos bracket open x plus b. So we are asked to form differential equation from a cos bracket open x plus b. Now we can do a whole lot of manipulations here. So what we do is that to form differential equation from this, we name the main equation as our equation 1. Then what we do is we have to look for the arbitrary constants, the number of arbitrary constants. So we have a being the arbitrary constant, b also being an arbitrary constant. So we have 2 arbitrary constants. So we have to differentiate the equation twice. So in the first, so we have to find the first and second derivative. So we differentiate the first one for the first time. So we are differentiating y with respect to x because y is the dependent variable and x is the independent variable. Okay, so what we will get is, if we differentiate this, we are going to get dy dx equals to, now in this function, this is a trig function, but there is another function or another function inside the trig function. So this is a composite function. This is a composite function or a function of function. So if you want to differentiate this, what we do is we have to use chain rule. We have to use chain rule to differentiate that. Using chain rule, we can use chain rule in a very fast way. All that we do is from our basic chain rule or calculus. From our basic calculus, what we do is this. We have cos x plus b. To differentiate this, if you want to use chain rule, all that we do is we do this. Now you should be able to identify in this equation. You should be able to identify the inner function and then the outer function. There is a function inside another function. This is a linear function inside the trig function. So this is the inner and this is the outer. Now, so I call the outer one the mother, and then the inner function the unborn child or the baby. So it's like a pregnant woman. The composite function or function of function is like a pregnant woman carrying a baby. Okay. So if you want to differentiate functions like this using the chain rule in the fast way, all that we do is you cover the mother. You cover the mother and differentiate the baby. So if you cover the mother and differentiate the baby, so the baby is a linear equation, so a linear function. If you differentiate x, you will get 1. Because b is a constant, if you differentiate b, you will get 0. So we have 1 as our answer if you differentiate the inner function. If you differentiate the inner one, we will get this 1. Then you multiply it by, now you cover the baby. If you cover the baby, we can assume that the baby is now k. You can assume that this is k, a single variable k. So if you differentiate cos k, you are going to get negative sine k. So that is if we replace the x plus b with k, we are going to get negative sine k as our derivative. Okay, so then we multiply. So we have, but k wasn't a function, it wasn't part of the equation given to us. So after replacing it with k, we can rewrite this as negative sine k, because 1 times this is sine k. But what is k? K is x plus b. K is x plus b. So it's very important that when we are giving a function like this, you should be able to differentiate it using the chain rule in this way. Using this approach is easy. Okay, so this our derivative. So if we differentiate a cos x plus b, we are going to differentiate to get the inner function. We are going to differentiate the inner, so cover the mother and differentiate the baby. If you differentiate the baby, you will get 1. Multiply by, then if you differentiate the mother, we have the mother. So if you differentiate the mother, you get cos. Cos, when you differentiate cos, you get negative sine. Negative sine the baby, and the baby is x plus b. So we repeat the baby again, because the woman is still pregnant. And finally we get negative, and there is a. So it's negative a sine x plus b. So we have 1 times negative a sine, bracket will be x plus b, gives us a sine x plus b. And we have dy dx is equal to that. Secondly, we have to differentiate again because we had 2 arbitrary constants. So this can be our equation 2, and we will differentiate the equation 2 again because we have to differentiate the equation 2 times. So we differentiate again with respect to x. So we are going to get the second derivative here. So d squared y dx squared is equal to, so we are going to continue. There is no variable here, so we will still use chain rule because this is a constant. So this is still a composite function or function of function. So all that we do here again is to apply the previous rule, the first rule. We cover the mother and differentiate the baby. If you differentiate x plus b, we will get 1. Multiply by, if you differentiate negative a sine the baby, we are going to get, if you differentiate sine, you will get cos. So we have negative a, if you differentiate sine, you get cos, and cos the baby, and repeat the baby. The woman is still pregnant. So we have 1 times negative a cos x plus b will give us negative a cos x plus b in bracket. So these are second derivative. And since these are second derivative, the next thing we have to do is we have to proceed by eliminating the constants. Now, to eliminate the constants here, the easiest way, let's look at this equation 3. Let's compare this equation to the very first equation given to us. We will notice that the more you differentiate cos, if you differentiate cos, you get sine. If you differentiate sine, you get cos. So the function is repeating itself. So you notice that after differentiating it 2 times, we have cos x plus b in brackets, cos x plus b, and we have cos x plus b. So if you compare the two, we have cos x plus b, cos x plus b, and we have a also multiplying this. We have a also multiplying equation 3. So all that we need to do is we are going to replace. We want to eliminate. So we replace the function here, the expression here, a cos x plus b with y, because y was equal to all this. Y was equal to all this. So wherever we see a cos x plus b, we are going to use or replace it with y. So to do so, if you are able to do so, then we have eliminated the constants from the equation. Cos x plus b, we are going to replace it with y. So finally, we get the squared y, the x squared, is equal to negative, and then from equation 3 we have y is equal to negative a cos x plus b. So if a cos x plus b is equal to y, if the whole of this is equal to y, the square y, the x squared, equation 3. If the whole of this is equal to y in equation 1, then we are going to take this away and replace it with y. So we have y. So these are second derivative, and that ends the formation. So before the differential equation, now we have the second derivative. The second differential coefficient is equal to negative y, and that ends the solving. And so this is our differential equation. So we form differential equation to some extent in some problems is very simple. So solving differential equation is very simple. All that you need to do is to be able to identify the arbitrary constants present in the given equation. It is very simple. So let's look at this example. Assuming we are given r equal to a cos theta. Here we have r being the dependent variable, theta being the independent variable, and a is a constant. So this is an equation with only one arbitrary constant. So you have to differentiate the equation once. Now this looks like a graph, a cos graph. With center O and radius a radius angle theta, then the adjacent being r, and then the hypotenuse being a. So we have a being the radius of the circle that can be traced by the line. And then theta is the angle subtended or measured from the x-axis, and then r is the distance or the displacement of the point P from O, from the origin. Okay. So our main business is to form differential equations. So all we need to do here is we have to differentiate. So once we've been able to identify the number of arbitrary constants, we name this as our equation 1. There's no other simplification that can be done. Then we differentiate. So we differentiate we differentiate r with respect to theta. So we get the r, the theta is equal to, if you differentiate cos, we will get minus sine. So we have directly minus a sine theta, and this is our differential equation. It's simple. This is our differential equation, but it contains the arbitrary constant a. So we have to eliminate the arbitrary constant. So what we do is you name this as our equation 2, then eliminate the arbitrary constant. So to eliminate, this is not like the previous one we did, because we have, this is not the second derivative that gives us sine cos theta as the previous. Here we have only sine theta, a sine theta, not the same as a cos theta. They are not the same. So we cannot just replace a sine theta with r. So all that we have to do, we have to substitute. So, and then you change your subject and then substitute. So we make either a the subject form equation 1 or a the subject form equation 2. So we can make a the subject form equation 1, and it's simple. Make a the subject from equation 1. From equation 1. So we have, from equation 1 we have r is equal to a cos theta, and we are asked to make a the subject here. So to make a the subject, we have r over cos theta is equal to a. We can name this as equation 3. Now since this is our equation 3, we can put equation 3 into equation 2 to replace the a. All that we don't need to do, we have to eliminate. So put equation 3 in equation 2. So we have the r, the theta is equal to negative a. A is r over cos theta. So this is r over cos theta, then sine theta. Negative a is r over cos theta, and then we have sine theta. So this is a, and this the previous sine theta, and then this is the negative. Now we learned that sine theta over cos theta is equal to tan theta. So we know that tan theta is equal to sine theta over cos theta. So this will help us to get negative r tan theta as our final solution. So this dr theta is equal to negative r tan theta. That's our final solution.